Now, this problem, we've got a gun being fired at an angle of 60 degrees and it has a velocity of 120. And again, we're taking gravity being 10 meters per second. So, that square there. So vertically, what do we see? Because we want the exact time for the bullet to reach its maximum height. So, well, we start with vertically being the acceleration being minus 10. Again, we integrate. We get minus 10t plus the constant. Now, we can see that our vertical velocity from our initial position velocity, where the velocity is at the initial position, we get sine of 60 is the vertical velocity over 120, which would give us 120 on sine 60 for our vertical velocity, and sine 60 is root 3 on 2, so we get 60 root 3. That's where that 60 root 3 comes into play, and that gives us our constant of integration here. Again, we integrate, we get minus 5t squared, 60 root 3 gets multiplied by the t, and our second constant, and we take our second constant. We're not told anywhere about where we're starting, so we can take it as being the origin. So there's our position statement for our vertical position. Now, our maximum height occurs when the first derivative of y is equal to 0, the vertical velocity is 0, because once it goes up, it stops vertically, and then it comes down. So where does it stop? Well, that's where your vertical velocity is 0. So we set the vertical velocity statement equal to 0, and solve, and we get t is equal to 6 root 3. So there's the exact time for it to reach the maximum height. The maximum height then would be reached at that, whatever that value would be, at that time would be for y. Summing it in, expanding out, collecting our terms, we get 540 meters. So there's our time taken to get the maximum height and the maximum height from that one. This time we got an arrow fired at a velocity of 24 meters per second. And it's aimed at the center of a target 1 meter high and 35 meters away. So there's our statement, something like that. So 24 meters per second, 1 meter high is where we want to aim it, and 35 meters away. This time we want to find what the angle should be to get to that position. So again, gravity is 10 meters per second. So it needs to do a bit of work, because we need to start to equate some expressions. So we get the idea. It's 24 is the initial velocity. So that leads us to be able to get our vertical velocity and horizontal velocity from that statement. So we know x dot on 24 would equal cos of theta. So the horizontal velocity is 24 cos theta. Similarly, the vertical velocity would be 24 sine theta. So when we put it into our statements, we get our acceleration horizontally is 0. Our vertical velocity, so we get a constant there, and when t was equal to 0 for our vertical position was 24 cos theta. So that's our vertical, our horizontal velocity going on there. So it's moving at that constant 24 cos theta. Position statement would be 24t cos theta plus another constant. Again, we're starting at an origin, so the constant there is 0. So there's our position, 24t cos theta. Then we've got acceleration due to gravity is minus 10. So vertically it's falling, it's acting in the negative direction at a constant rate. Our velocity there would be minus 10t plus a constant. Again, when t was equal to 0, our vertical velocity is 24 sine theta. So there's, it becomes our constant there. So there's our statement for our velocity in vertical motion. Integrate again, minus 5t squared, 24t sine theta, plus another constant. And again, because we start at the origin, our constant there is 0. There's our position statement for our vertical motion. Now, what does that mean for us? Well, we know that when x is equal to 35, we get y is equal to 1. So, that means we can write 35 equal to 24t cos theta. So it allows us to get a statement in terms of t. We've still got theta in there, so we just can't solve that one. But that allows us to eliminate t from because we can eliminate y because y is equal to 1 at the same time, we can take this value of t and put it into this expression. And now we've got an expression with only theta in there. And that's good. If we're going to find the angle, that's what we need. We need an equation with just theta in there. Now here's where it gets a little bit tricky, because now we've got to get a value for theta from that. So what's that do for us? Well, we keep our 1 out there for the moment. We've got to square this side. So we get 35 on 24 squared. 1 on cos squared theta, which becomes our sec squared theta. We've got 35, and the 24s will cancel, and sine on cos becomes tan theta. So there's the statement cleaned up a little bit, but still in sec squared theta and tan theta, which poses a little bit of a problem until we do this manipulation and get it all in terms of tan theta, because we can change sec squared theta to 1 plus tan squared theta. We bring the 1 across as well. So it starts to look like, and well, it doesn't start to look like, it is a quadratic equation there. So it's a bit ugly, the numbers are not fun, but it's still possible to have our quadratic there. So we solve our quadratic for tan theta. So what do we get? We get minus 35 plus or minus b squared minus 4ac, so we sub all our values in. And when we do that, we end up with two values, tan theta being equal 0.2569 and theta being tan theta being 3.03344. We take the inverse 10, we get 14 and 72, which means we can launch it at two different angles. We can launch it at two different angles, one obviously more shallow, the other one steeper, but they will both be able to travel at 35 meters away, hit that target at 1 meter high if the velocity is initially 24 meters per second, and that's what the arrow is going to be fired at, and either at that angle or that angle it will hit the target. So it'll have two different projections. So one will be flatter for 14 and that one will be higher and then come down, but it'll still hit that target at the same time. So that's where we get with that problem. So check that one again. That one's not easy. Lots of manipulation going on. You've got to be really careful with all these values that we've got there. The last question we've got. This time we've got a horizontal drain pipe which is 6 meters above the sea level. An empty stormwater into the sea. If the water comes out horizontally and reaches the sea 2 meters out of the pipe, find the initial velocity of the water. Now, what we're looking to do here with this one is this is our situation. The water comes out, and it comes out horizontally, which means there's no vertical velocity to start off with. So it's just all initially horizontal. It's 6 meters above the sea level, and it reaches 2 meters out there. So we're not starting from our origin position again. We're starting from up here this time, and because it's just dropping, there's no actual vertical component to our velocity initially. There will be as we go, but it's horizontally, it's going to be just v. So that's where we are able to do that. So if our initial velocity is v, that would only be the horizontal velocity. So we're able to get our statements. Again, we start with acceleration is 0. The initial velocity would, horizontal velocity and velocity all up would just be v. And so we get vt plus our constant. But again, we start with x is equal to 0. So our constant there would be 0. So the position for x is just x is equal to vt. Vertically, we start with minus 10. Because there's still gravity acting on it. That's why we'll just go out and start falling straight away. And we get our velocity statement, integrate, get our constant. But this time when we get t is equal to 0, our initial velocity vertically is 0. So our constant's 0. So we just get minus 10t. We integrate that, we get minus 5t squared plus another constant. Now this is where it's a little bit different, because when t is equal to 0, the height now is 6. It starts from a height 6, so we get our constant of integration this time being 6. So what we want to do is find the initial velocity of the water. So we know that when y is equal to 0, so where it lands, x is equal to 2. So if that's the case, we're able to set up and find a value for time that will happen, because we are able to get x, when y is equal to 0, we get our time of root 6 on 5 seconds. And we know that when it hits the ground, when it hits at root 6 on 5 there, and it lands 2 meters away, so x is equal to 2 when t is equal to root 6 on 5, allows us to multiply through by the root 5 and the root 6 and get our velocity as 2 root 5 on root 6 meters per second. So it's a little bit different because it's not having a starting position at the origin, but it's somewhere up there. So we see that we have to get different constants there. All those questions rely on the same thing: getting our statements for acceleration, velocity, and position for both horizontal movement and vertical movement. And then if we need to relate them, we can do that. Sometimes that's easy, sometimes it's hard, depending on what we're trying to find and what data we're given in our problem.